Hello everyone and welcome to the latest SNIA Ethernet Storage Forum webcast. This is everything you want to know about storage, part teal, and this is the buffering pod, though we will be covering much more than just buffering. So we will be getting started here. I'm excited to say that we have some great speakers and great topics here today. But before we get started, let me cover some basic logistics and housekeeping required for all our webcasts. First of all, this is the standard SNIA, Storage Networking Industry Association legal notice. Just a friendly reminder that the material in this presentation is copyrighted by SNIA, unless otherwise noted. Any member company of SNIA may reuse the material in this webcast in presentations or literature under the following conditions: that any slides must be reproduced in their entirety without modification, and SNIA must be acknowledged as a source of the material. This is a SNIA project. However, nothing in this presentation or none of the presenters are attorneys, and none of this should be considered as legal advice. The information presented in this webcast represents the author's personal opinion or a combination of personal opinions and current understandings, and while we make our best effort to make it accurate and relevant, we do not assume responsibility or liability for any damages, so use this information at your own risk. All right, with that friendly disclaimer out of the way, let me just remind everyone that SNIA is a very active and popular organization in the world of storage networking. We have more than 160 member companies, more than 3,500 active members, more than 50,000 people in our audience worldwide, and you can learn more about this if you go to the SNIA website at snia.org/technical. And we encourage any of you who are not members of SNIA to consider joining. Membership is very affordable for individual members as well as for organizations. And there's access to material and the chance to participate in discussions of standards and to produce webinars such as this one. All right, that said, welcome back to the webcast. Happy Halloween, everyone. Oh, wait, I mean happy Valentine's Day. So I hope those of you who need to are planning whatever activities need to be done for Valentine's Day. But first, learn more about buffering, caching, I/O queues, and flow control with our experts, who are today Mark Rogov from Dell EMC, David Minturn from Intel, Rob Davis from Mellanox, and I am your moderator today, John Kim. Today's agenda is we're going to talk about queuing, buffering, caching, and flow control. And these are all very important to storage networking, to storage in general, and especially to understanding and maximizing storage performance. So first up, with Dave Minturn from Intel, is queuing. Dave, please go ahead.
Good morning, good afternoon, everybody. I'm just going to cover queuing, and then this will lead into, Mark will cover the buffering and queuing after this. So first I want to start with some definitions. And one of the items when everybody talks about storage queues is queue depth. So I wanted to make sure everybody had a clear understanding what that definition was. So there's really three components. One is an I/O operation. You know, what this is a storage operation that's issued by the host or an initiator to a storage device or system, typically called targets. An example would be, a host issuing a read operation for 100 blocks of storage from a storage device. An I/O queue is a queue which holds one or more outstanding I/O operations. So once the host, the initiator, has issued it, it's considered outstanding until it completes. The I/O queue depth is the maximum number of outstanding I/O operations that the I/O queue can hold. And I'll go through a couple examples to clarify that. So the next thing is I/O queue depth example. What I'm showing here on the left is a host system initiator. And I'm showing an abstract I/O queue that is in between the storage device and the host. And what you're seeing here is an example of a queue depth of 3, where the green I/O operation, once the host issues it, it becomes an outstanding I/O operation resident in the I/O queue, and then the storage device would eventually service it and complete it. in this example, you're seeing a green, a yellow, and a blue. So 3 outstanding I/O operations being held by the queue. All those would be serviced and then completed back to the host. So this is an example of an I/O queue depth of 3, where you see 3 outstanding operations in the queue. Digging in a little bit more deeply, okay, why do I need more than one outstanding operation? So really, this all is about parallelism and sort of overlapping the execution of the I/O operation in order to get better performance. And so what I'm showing here is an example of a storage device that has been fed 3 I/O operations: the green, the yellow, the blue. And the back end of that storage device in this example is, let's say it's a bunch of media that allows for parallel execution of those 3 operations. So in this example, what I'm showing is these I/O requests are arriving at the storage device in about 10 microsecond interval, and then they're all being serviced. The service time for that back end is 100 microseconds. Then what you're seeing is after 30 microseconds, all 3 of those operations are going on in parallel, and then the completion of those are happening at the same rate as the arrival rate. So what you're seeing is completion every 10 microseconds. The result of this, if this device was only able to have a queue depth of 1, what you'd see is the overall service time would have been 100 microseconds for that operation, and the device would have run about 10K IOPS. When you get a queue depth of 3, what you're seeing is overlapping. So these 3 operations are all happening in parallel, and then the completion of all 3 happens at 120 microseconds. And in this case, the IOPS for this is at 25K. So this is sort of a simple example of why you would increase queue depth based on, what your I/O device or how many operations you could have going in parallel. So some considerations with the queue depth. I showed a very simple example in the previous one between the host and the I/O device. In reality, what you see on a host system is there's typically lots of autonomous processes running simultaneously, whether this be a single application with a lot of threads or maybe a virtualized system with a lot of VMs. What you see is all these are issuing I/O operations, and these I/O operations are sort of aggregating through the host OS stack or through a hypervisor down to the storage device. And so in this case, what you have to be considering is, what is my queue depth at each one of these layers along the way? For instance, how many I/Os is the application issuing to be able to get, a higher amount of I/O operations? Also, what's the OS doing? Does the OS have enough buffering or queuing, to accommodate this amount of autonomous process? Same with the storage device. And then ultimately, even on the storage device itself may have some queue depth limit that needs to be examined if it's not achieving the expected IOPS. So essentially what here is, the main point is the queue depth must be looked at as an end-to-end type. So look at every layer from the application all the way to the storage device. This includes the OS, the storage device, and the media.
David, does that mean that the different queues can actually exist in more than one location? There's not just one queue, that in the I/O chain from end to end, you could have multiple queues?
Yes. Yeah, there can be multiple queues along the way, and the queue locality, depending on, the technology you're using, sometimes the queues are over the host system, sometimes the queues are over on the storage device itself. So you really need to, be aware of what that end-to-end model looks like for the system that you're using.
Is it possible to say that the total queue depth is simply adding up each of the queues in order, or is it more complicated than that if you're analyzing what your queue depth is and how it affects your performance?
I think it's a little bit more in depth than that. What you have to do is understand what queues are in between the application and the storage device, and look at each of those. If there's settings, for instance, that say, for instance, the host will only allow up to a certain amount of outstanding operations, but then that's less than what the device could allow, for instance. You really need to be aware of where are all those elements of queuing and which ones to avoid as well. that you want to make sure, like for instance, your storage device queue is properly sized to not have the host OS queues, kick in and start buffering, because that's a less efficient model there. So it really is, there are really several different areas of queuing. And then again, the application. If the application only issues one I/O, it doesn't matter what your queue depth is, if that's you're trying to get performance out of that one application. So that would be sort of like application queue depth is how many I/Os is it issuing. So it's really, it's really in different areas.
Got it. Okay, very helpful. I just want to remind the audience you can ask questions with the online question tool. I see the questions are just starting to come in, but please don't be shy. We said you don't have to be too proud to watch this webinar. Please don't be too shy to ask questions, and we will direct the questions to the appropriate presenter as quickly as possible. Dave, please go on.
Okay. Yeah, one thing to consider with the QDAP, since you've asked, most of the modern storage devices, either VHBAs or let's say NVMe SSDs, they have multiple queues for efficiency. They typically use this to avoid contention on the host side between the host CPUs. So when you're looking at the queue depth at that level, either at the HBA queue or the storage, say an SSD queue, you really need to account for all the different queues that are in place there. So, for instance, if there's like 5 queues, increasing the queue depth, you get to have that many more resources involved in that much queue depth. So essentially what you have is an effective queue depth is the sum of all the queues to that storage device, in the case you have multiple queues. Okay, another consideration with the queue depth, and we're touching a little bit on some buffering, is an outstanding operation typically from the host, once the host issues that outstanding operation, there's a transfer buffer that's used for either, sending the data out to the storage device or receiving the data back from the storage device, and then likewise on the storage device itself. These buffers pretty much stay committed through the life of the outstanding I/O. So if you're increasing your queue depth, of this I/O device, and let's say that each one of those outstanding operations can do maybe up to 64K of I/O, you really have to account for that much buffering, being sort of committed while those operations are happening. On the host system, you typically have a fair amount of memory there where it's not as much of a concern. In certain cases, those buffers may be over there on the storage device, and that storage device may have a limitation as to how many of those buffers or how much space it has to actually do that much buffer, how much memory it has. So what you want to do is, as you're sizing the queue depth, just be aware of that, that your I/O queue memory is essentially, the size of the queue depth times, the IOP descriptor, which is usually small, but this transfer buffer, which is typically large. Okay. So I'll move on to Mark.
Okay, actually, before we go on, we have a couple of audience questions. So Dave,
okay.
Let me send a few of those to you, and then we'll go on to Mark and caching, because we know everyone likes to have a lot of cache. Cache is king, as they say. But back to queuing, one question simple is, does the SCSI protocol have a max queue depth, and is that maximum 32?
The SCSI does have a max queue depth, and it would not typically be 32. I think where we used to see 32 was more on like HCI, queue depth. I'm more familiar with the, with the SSD interfaces and that, where we moved from HCI, which was a queue depth of 32. That's what that max was, to a multi-queue model where the queue depth is 64K. So there's a significant change from that perspective. I do not believe that queue depth 32 in SCSI is the limit. It may be some implementation.
Okay. Another question is, would you use a queuing algorithm to manage I/O queues, or the I/O queue? And if so, what algorithm is used to manage that queue?
Yeah, that's actually sort of a good question. I think typically the way experience has shown that vendors, of the storage devices typically rate, either the storage device or let's say an SSD based on, a queue depth. where you'd see, okay, at QDEP1, for instance, you're going to get this because that's the latency of the operation. And then as you start to see some of these devices with a lot of parallelism or a lot of media parallelism, they get up to QDEPs of say 32 or maybe even 64. It's possible. I think some algorithms may take place, but I think typically, what I've seen, it's been sort of static allocation, based on based on what the device itself or the target itself supports.
Okay, very interesting. There's one more queuing question, then we'll move on, and then if we have time at the end, we'll return to the other queuing questions. The last queuing or queue depth question is a bigger queue depth always better, or are there cases where making the queue depth really, big, just a bit deeper and deeper could actually slow things down?
It's actually sort of comes down to resource usages. That there is a finite amount of resource for the queue depth, and making it larger. Sometimes some of this is what you see happening is a little bit of some legacy applications, that were typically run, let's say, on sort of higher latency devices like hard drives and things like that, that have been written to have very, very large queue depths. And what's happened with large queue depth on the application side, it is less efficient of managing all those outstanding IOs and the associated threads. Because each one of those threads, each one of those outstanding IOs has resource associated with it. May do some cache pollution over there on the host based on how many outstanding you have. So really the best thing to do is to keep it as small as possible. And then also what you're seeing sort of in the industry is newer style devices with media that allow you to get maximum IOs at a much smaller queue depth, where it isn't so resource intensive.
Got it. So it seems that we want the queue depth to be deep enough or big enough to get the most performance out of the device, but the bigger it is, the more resources it uses. So we only want to make it as big as needed to maximize the performance of the storage.
Right.
Okay, Dave, thank you very much. We're now going on to Mark Rogoff of Dell EMC, who will talk about cache, and then, believe it or not, after that, Rob will talk a little bit about credit or credits. But Mark, please go ahead and tell us, why is cache king, and where can I use it?
Thanks, John. My name is Mark Rogoff. As you said, I work for Dell EMC, and I have to say before I start, hi, Mom. Thanks for bringing our extended family here. This is really going to help us in the ratings. And unfortunately, the cache that I'm going to talk about is not money. The cache I'm going to talk about has to do with something else. And I don't know how everybody else learns things. I always like to learn new subjects, and I try to get some mental anchors about what it is and how it is. So what I did is I typed cache in Google and quickly realized that there's 3 towns in the U.S. that are named cache. And I thought that's kind of interesting. I didn't expect that to see and to be the fact, but there's even a cache peak. There is a cache county. So there's a lot of caching happening in the U.S. And if anything you guys are going to remember from this session, at least you can remember this map, even though it has nothing to do with the subject that we're going to talk about. But cache, the definition, also known as a cache memory, comes from the fact that it's a temporary location, or we like sometimes call it auxiliary memory, from which the high-speed retrieval is possible. And if you think about it, that's where we place stuff or data in the computers to be able to retrieve them faster than where that originally resides. To paint a better picture, imagine we are watching Netflix. And I'm kind of drawing here, expecting that everybody in the audience knows what Netflix is. But if you don't, it's a streaming service. And when you watch a movie being streamed over to you, the data consisting for the movie is being passed across the internet. One thing about the internet is that the speed of the internet varies, and it varies all the time. And what you can possibly have happening is that one packet could be sent at some point, and the other one could be sent after it, but the second would arrive before the first. Just happens to be with the quality of the internet, the routing path, and everything else that happens in between. And along comes the buffer. The buffer is a little device or a little memory area that you will have at your home. And if you think about it, it's placed somewhere inside your modem if you're using internet. And the buffer is similar to cache, yet it is not the same thing, because what's going to happen, buffer is going to be used only once for every single package. And it's used to rearrange things. It's a short-term thing, and we're going to talk more about the buffer. And I think the whole session was themed to be kind of buffering pod, even though the buffer itself is super, super tiny. But when you think of my picture, you have the 3 packets coming in, they get rearranged in the middle, and then they get rearranged back into a contiguous movie picture in order for someone to be able to enjoy Avatar. This picture gets a little more complicated if we assume that there is multiple people watching the same movie from the same service. And one thing you might notice on the right is that there is a fair amount of the same information being sent to all 3 of my users, yet every single one of them has their movie at a different spot because they started at some later time or not. They just happen to be in a different placement of it. And every single user is going to have their own little buffer used to reorder and reorganize the packages that have been delivered. However, when we look at the Netflix side, what Netflix is going to say is recognize the fact that all 3 of these users are receiving the same data. In fact, some of the data that they're receiving is exactly the same, it's exactly the same blocks. So instead of keeping that data out in the spinning media somewhere, which Netflix definitely uses spinning media, they'll be placing that data temporarily inside the cache for the purposes of being able to send the same block, the same piece of data to multiple users without going back to the disk. And this multiple reuse of the data is really what quantifies what cache is. Now, diving a little deeper, when cache was first created, it was created because back in the day, we had these things called spinning drives. And I'm sure some of you might be kind of chuckling here, but these days, spinning drives are considered to be a little bit of a misnomer because we live in the flash world. But very early back in the days, we didn't even have drives, we had tapes. I'm sure most of you have seen these big pictures of magnetic tapes. And the point was that the data stored on the slow spinning media was slow to be retrieved. And the idea of cache was born to say, why don't we store some data not in the magnetic spinning media, but somewhere in the silicon on the computer itself to make it faster achievable to the application or to the host. So the first reason why caches were put in place was for this term called a read hit. And this term is what I have depicted here in the picture. When the host or an application sends a request to get a piece of data, and it get immediately response back from cache saying, there you go. They were able to hit exactly the data sitting in cache, known as a read hit. What happens when the data was not in cache? That's known as a read miss. That's a very cache-rich terminology. And what all that means is when the host requests the data from cache, cache doesn't have it. So cache has to go to the disk and read that data from the disk into the cache, and then from cache, the data will be sent back to the host. Clearly, if you think about it, read hits are a lot faster than read misses. Every time you have a read miss, application has to wait longer to get its data. Now on the writes, things are a little bit different. Whenever a write is coming in from the host, we have a term defining what's going to happen with that. And cache typically consists of memory that is not powered outside of normal power source, or it's volatile. In other words, if something happens to cache, we don't back it up and that data might be lost. So what happens in computer systems, we have to write through cache, meaning that the data is sent from the computer to the cache, from cache to spinning media or some other long-term storage place. And only then do we acknowledge back to the host that the write is safe. It takes some time, and writing through the cache is actually a little bit slower than writing directly into the drives because you have this extra step. But that step is imperative if we really care about the data that we're trying to write down. Alternatively, there is a way to bypass cache altogether called write around or write bypass. That's when the host sends the write directly to the disk, and in the order that it's sending down there, it's demanding to bypass cache altogether. This is used for large writes. So if you think about it, cache is memory. Memory has limitations. It could be 256 gigs of memory that you allocated for cache. Nonetheless, you may not want to fill it up with everything that's going on. For example, you may have an application that writes data and doesn't ever read it back, and it also writes it in large chunks. In these cases, we have the availability to write around cache and bypass it altogether and go directly to the disk and wait for the acknowledgement to come back. With large IOs, it may be even faster to do it this way than writing through cache when we keep a copy of data in cache. And the last one, but not least one, is the second reason why cache exists. And if you think about it, this is the reason that most vendors, most storage solutions at this point emphasize back to the customer. And this is called write back. This is when the host sends the IO to cache, and cache immediately responds back to the host saying, I got it, go ahead and write another one or read it and do whatever you like to do. Delaying the time when that data is then written back to the spinning media or some long-term media, and therefore speeding up the host performance. So if the host is using write back and is getting a whole bunch of read hits from the application point of view, their performance is the best.
Mark, very interesting. Let me ask you, let me go back to that slide for just a second and ask a couple of questions about caching. And by the way, a few people have asked, will they be able to get the slides or will they be able to get access to the presentation? And the answer is that yes, almost just a few minutes after we're done with this webcast, the slides should be available online through BrightTalk. But back to caching. So Mark, I often thought of cache as a way to put the data closer to the user or closer to the application. Are you saying, is a cache always closer to the user, or could it just be a faster storage, or could it be both?
It's actually a very good question, and I'm going to be answering that question in a couple of slides. But the short answer is it could be anywhere. I'm giving you a very simplified example of how cache works without necessarily placing that either at the host or at the drives or somewhere in the middle. In reality, if you think about it, it is somewhere in the middle because you can probably hit it as the I/O is going from one side to the other.
Okay, I didn't mean to get ahead of your slide there if you're going to cover that, but another question would be, in the world, you mentioned that not everyone's using the spinning disks anymore. If someone has a solid-state disk made of flash, is there still a role to play for cache? If I have all solid-state media, could I still benefit from, my performance still benefit from putting a cache somewhere?
Correct. And that's something that a lot of people might be confusing. And the short answer, yes. Your RAM, which is typically where modern caching is sitting in there, is still an order, if not 2 orders of magnitude faster than your solid-state disks. And I think Jay Metz, who is kind of the father of this entire series, he once explained it in a very good fashion. He had this whole presentation where he was comparing the L1, L2, L3 caches we have on processors, and then moving on to RAM and moving on to the physical media as to delivering pizza. And the order of magnitude difference between delivering pizza means getting pizza within half an hour of you getting an order, or getting pizza next year after you ordered today. Imagine how cold it might be, would argue Jay. The same thing is relevant today between RAM capacity, where we put the cache, and any kind of long-term storage capacity, be that solid-state drive or spinning drive. Of course, solid-state is going to be a lot faster than spinning drive, but both of them are indistinguishably slow from the point of view of RAM.
Got it. So even if I have an all-flash array built with solid-state, well, built all with flash, I could still benefit from a cache because the performance of RAM is still so much faster than NAND flash.
Absolutely correct. You're going to be benefiting from cache, to reiterate, if you're going to be having a high rate of read hits, and you're going to be able to use write back. If you hit both of those, cache is going to help you. If, however, your workload is going to have very low read hits, and you will have to write around cache all the time, then having cache is not going to benefit you. But then argumentatively, the price of having it there is going to be still negligible compared to the time it takes to go to the solid-state drive or to a spinning drive. So you might as well have cache in case you do have a spin-up within your workload where read hits or write-backs is going to be beneficial.
Got it. Very interesting. Okay, I think there'll be a few more caching questions at the end of your section, but for now, please go on.
Okay, so enough theory. Let me show you a little bit of practical difference in here. What I have in here is a graph that Ken Cantrell, my co-presenter for another session that I run with SNIA called Performance Benchmarking, he wrote a script, and that script was testing how long does it take to list a number of files in a directory and when we increase number of files. So here on the y-axis on the bottom, you see how we go from 20,000 items in a folder to 500,000 items in the folder. And we were modifying the script a little bit, and we got two different results, right? We have the y-axis, y-line going down there close to the y-axis, and the x kind of going up high. And the question I'll have back to everybody is consider these two graphs and tell me what's different about them. Is there something relating to the subject that might be different between the two? And John, since you are the only one who can communicate with me, I'll ask you that question. What do you think? What's the difference between X and Y?
One person was watching Avatar, and the other person was watching an old TV series called Buffer the Latency Slayer.
Or they're on Google Maps trying to find cache town halls. The reality is the difference is...
Let me take another guess. Okay, go ahead.
Yeah, the difference is caching, and that's what I was driving towards. On the bottom, we have the results when caching is enabled for the operation of listing the contents of the directory. And then on the top one, we have when caching is disabled. Now, we're running this on multiple different systems, and we were kind of utilizing all the results together. But you can see that if you are not caching the data, the more items there are in the directory, the longer it takes for the simple listing command to complete, which kind of makes sense, right? Because the system has to go to walk through every single item in the folder and has no reference to the fast cache storage if it was able to walk that faster. And that's effectively the smallest, simplest example you can look at and say, how beneficial is it to have cache or not? And a general example is having cache is a good thing. Chances are that you're going to be hitting some same of the data. Your application might be calling for the same data you was just using before repeatedly. So having it hashed out somewhere along the way is a great thing. A lot of vendors in storage world have the cache and they emphasize how speedy their solution is without necessarily explaining that that speed is relevant for caching that they are doing internally. And kudos to them, this is all good. It's really a good thing when technologically we're able to use technology to speed the application. We don't necessarily always have to explain how that works. And going kind of back to the question, John, that you asked me, is where do caches occur? So if anyone on the phone is ever going to interview at NetApp, where Ken Cantrell works, and as I said, Ken is my co-presenter for the series that we have, Ken has one interview question, and here is the answer to that interview question. So if you're ever going to see Ken, and chances are he's going to ask you, and the question is going to be just like the one you said, John, where does caching occur if one considers the entire solution under test? And the answer is caching can occur everywhere. We have caching at the client side, and it's there in multiple places. For example, it could be there just because you have your local RAM and you have local caching on that RAM for operating system, things like listing and directory side. You can have caching within the browser. You can have caching within the networking protocol of communicating to somewhere else. If you leave your host, there is sometimes caching on the interconnect between the client and your storage controller. There's always a massive storage controller cache. There could be cache on the back-end interconnect of that storage controller, especially if you think about it, some storage controller allows saving data in the cloud today. There's definitely somewhere cache along that path. And last but not least, there are caches today inside modern enterprise storage disks, whether they're solid state or whether they're spinning. Chances are there's going to be some silicon in there that's acting like a cache. Now at the disk, you can argue and say that that's more of a buffer and less of a cache. But when we talk about the proliferation of temporary places inside the solution under test, they can take the data and allow that data to be retrieved fastly. Then we're talking about the caching mechanism. And that's what I would like to finish my section with.
Okay, very good. So it looks like you always want to have some cache, that the cache can be in multiple places, and hopefully Ken is not too upset that you gave away the answer to his interview question. You know, now he might have to come up with a new interview question. Speaking of questions, there are about 3 questions about cache, so I'm going to give you one of them now from the audience, and then we'll maybe save the rest for the end, assuming we have time. So there's one question about write caching or filling up the cache. What if I have really large-sized writes and they fill up the cache quickly? Is there a way to avoid that or to bypass the cache for large-sized writes?
Yes, and there is a way. And you're trying to really ask an implementation question. So from cache's point of view, that question has very little relevance. We're either going to accept the write or not. And if you think about it, if cache is busy and incoming I/O comes in, cache needs to be cleaned up. And there's a whole concept of managing the capacity within cache itself, on how fast can we clean data up. And there's different algorithms we can put in there. We need to free up the space using whatever algorithm we prefer. And then once space is freed, allow the new write to commit. Now, storage vendors have an ability to control that a little bit outside the cache as well. And sometimes they have settings that say, hey, if the I/O size is larger than a specific number, let's say 1 megabyte in size, we're going to force that I/O to bypass the cache, period, and not even bother with that. But it's a vendor choice. It's not something necessarily that the host can control.
Got it.
Now,
okay, very useful. Okay, thank you very
much. Go ahead.
I
think that's a good answer. I should stop there before I go too deep.
All right. No, it's just also we want to make sure that we get through all of our topics and then have time for questions at the end. So now let me turn it over to Rob Davis of Mellanox to talk about flow control and, in fact, how that might affect buffers or caches. Rob?
Thank you, John. Hello, everybody. As John said, I'm going to be talking about flow control. So we're going to start off with the definition. So the technical definition, mechanism for temporarily stopping the transmission of data on a computer network to avoid buffer overflows. So that's the technical definition. A more practical way to look at it. Here is no flow control. And here's flow control. So let's start out by talking about the buffers that flow control is meant to protect. So these buffers are a little bit different than the buffers the other presenters have talked about. These are buffers in the network devices, and they're basically everywhere. All the different pieces of components in a network have buffers in them, and they're there for speed matching. So basically, if you have 10 gigabits in and 40 gigabits out, you don't probably need buffers, but if you have 40 gigabits in and 10 out, you do. And so that's where the speed matching comes in. But as in most cases in computers, there's never enough memory, or in this case, enough memory for the buffers. And so what can happen if something isn't working right in the flow control, you can end up with what's called buffer overflows. And this happens when there isn't enough memory in a buffer to do that speed matching, or there's for some reason, data has stopped flowing in a certain direction. In Ethernet, this is actually acceptable in a normal condition that can happen. And there's upper level protocols that in the software of the computers that can handle this. But it does cause that these network devices to drop the packets and force those upper level protocols to recover. And it can even force applications to have to recover from packet loss. And all this, of course, decreases the performance. So in general, buffer overflows are bad. So going a little deeper into why buffer overflows happen, let's look at the example I talked about earlier. And here I have some a group of servers that are putting data in to a switch at 25 gig, and we have an older storage device that's connected at 10 gig. And if, it's pretty obvious that if there's too much traffic coming from the servers, you're going to overflow the buffers in that switch because they can't deliver the data to the slower 10 gigabit device. And this is where flow control comes in. Going back to the definition, to temporarily stop the transmission of the data. This mechanism here was standardized by IEEE way back in 1997, and it's perfectly named pause. I'm going to go through a couple of different flow control methods. There's many more. And one thing that's important to note is the upper level software and even applications, for example, the Netflix application that were talked about earlier, have other flow control mechanisms. So there's lots of them occurring. The ones I'm talking about are in the network devices. So what happens with pause is when it's turned on in a network device, like a switch, for example, it watches the levels in its buffers. And when a preset level is hit or reached, it sends a pause message to the next device upstream, and that tells it to stop sending data for a specified amount of time. And that time in the pause, in this particular method, is based on a number of bit times. So it sort of will match whatever the speed is in a way. Looking at a couple of other technologies and how they do a flow control. So this is Fiber Channel and InfiniBand, and they both have a little bit different approach. It's called a positive or credit-based flow control. And basically the message, the sender of the message before it starts sending data knows how much buffer ahead of time that the receiver has. And this is done with a handshake at initialization. So for Fiber Channel, it would be at fabric login, where both sides exchange the size of their buffers. And then it updates the sender of data as messages are received, as messages are passed on. So if the sending device knows that it can send, 10K of data, and it sends that 10K until it receives a message from the receiver that more space is available because the receiver has passed that data on to the next upstream device, it won't send any more data. And therefore, this prevents overflows from happening.
Got it. So Rob, you're saying that with the pause that you showed first, I wait to see when the buffer gets to a certain threshold and it's almost full, and then it tells the sender to pause. Where with credit-based flow control, before I send it, I know how much space or how much buffer space is available on the other side. Is that right?
Exactly, John. So it's just two different ways of approaching this, solving the same problem. And obviously, you can see there's differences in the efficiency of both, but both of them work.
Okay, great. Thank you.
And one thing to mention about the positive flow control, Fiber Channel does this, and as well as InfiniBand does it. So the standards, if you want to look into more details on this, would be found in T11 for Fiber Channel and the IBT for InfiniBand. So there's another kind of flow control. This one is an example in Ethernet, and it's called ECN, or explicit congestion notification. And it works differently than the other flow control methods that I just talked about so far, because instead of stopping the sender's data flow, it just slows it down. So here's how that one works. So instead of a pause message or that's sent to the sending device, the device that's experiencing the nearing of buffer flow, overflow, or has a threshold setting that's been preset. When it gets to that threshold in the buffer, that device then basically sets a bit in the messages that it's sending out of that buffer. So it says, hey, I'm starting to fill up. I can see that I don't have much more room, so I'm going to start setting this bit on all the packets that I forward. Now, when that packet ends up in its destination, that destination then sends a message back to the sender, and that sender, when it gets that message, reduces its transmission rate to that destination. So it's a much more controlled method that is designed to try to identify the culprit that's sending too much data and have it slow its transmission rate rather than stop it altogether. And it also doesn't stop all the devices as a buffer flows. It tries to identify the explicit device causing the congestion. Now there's another kind of flow control, and it's to get around the problem all of us face who travel for business a lot, and we get to the airport and it's spring break, and it's called priority flow control. And how priority flow control works, and this is an example of priority flow control in Ethernet, and it's called PFC. Funny, the acronym matches exactly. And it was designed in Ethernet originally for fiber channel over Ethernet, which required a more detailed way of stopping data for storage where you had priorities between standard Ethernet traffic and storage traffic, which you wanted to probably have a little bit more priority. And so the way it works is very similar to pause, except there's up to 8 priority levels. And each level has its own buffer. And this is controlled with a pause only for that buffer. So this means you can stop some traffic while allowing other traffic to continue. So those are some examples of flow control. And like I said, there's many more, and also there's upper level software doing flow control that, that we weren't focusing on in this talk. And with that, I'll turn it back over to John.
Rob, thank you. We have a couple of questions have accumulated here in our question buffer. So I'll be the question flow control and figure out and prioritize which one goes first. And let's start with one question, Rob, for you. Is it mandatory for all devices in the network, the host and storage, to have the same speed ports? Because you have an example where they might have different speed ports.
Absolutely not required, and that's what flow control is here to enable. So examples would be older Ethernet storage on iSCSI that had a 10 gigabit connection, or servers that were at 10 gigabit with newer storage that was at 40 or 50 or even 100. And so you have different speeds between the storage and the servers that are accessing it. And this is common through all technologies, whether it's all technologies where storage is involved, whether it's fiber channel, Ethernet, or InfiniBand, or anything new.
Okay, great. Another question for you, then I'll do some wrap-up slides, and we'll go back to more questions for the other presenters. So, Rob, the question is, do server devices automatically honor the pause frame, or do you have to configure them to honor the pause frame or pause command?
They have to be configured, as well as the switches. So you need to, if it's required for your particular application, for example, using very high performance storage like the new NVMe over Fabric, because the latency is so low and the performance is so high, you really want to make sure you're not overflowing buffers in your network. So you want to make sure that you've chosen a version of flow control and implemented it if you want to maintain that high performance that you just spent a lot of money on buying. Great.
That answer makes a lot of sense. Okay, let me do a quick wrap-up, and then we will have time to take a few more of the questions, because the questions are starting to pile up here behind the dam. So summary of our presentation. So queues are a way to line up work processes or requests, and they can let you get more work done with parallelism. Okay? And then buffers are a way to absorb traffic bursts and smooth out data flow, and also reorder data in case the data might get out of order on the way. And caches are a way to store data either closer to the user or closer to the application, or store it on faster media, faster location, or both. It could be faster and closer to the user. And one difference between the two is that buffers tend to have their data used just once, where caches can have the data, if it's popular data, be used over and over again, and that's part of their efficiency. Flow control is a way to modulate or control the rate of data flow or the number of requests in order to prevent buffer overflow, because buffer overflow can lead to lost packets, which can then lead to slower performance. So that's a quick summary of this. Let's move on. A couple more things. We have some other great webinars coming up. So if you found this interesting, this is just one of a series of webinars called storage terms you always want, or storage questions you always had but were too proud to ask. So for example, we have another one about iSCSI coming up on March 2nd. And we have some previously recorded ones in this series. Each one is coded with is color-coded. So this was part teal today, or this is previous, and part rosé is coming up. We had previously done chartreuse and mauve, and those can be found either on the Bright Talk website or found through the SNIA ESF page on the Webcast section. We also expect coming up, we'll have one called Vermilion, which will be what if programming and networking got together and had a baby. And then one called Turquoise, which will be about where does my data go, and you can see that will cover like volatile versus non-volatile memory, NVDIMM versus RAM versus DRAM, different types of flash, and so forth. We also have coming up, or we also have a series of storage performance benchmarking webcasts, which are done by Mark Rogov and Ken Cantrell. And those talk about different types of storage performance, including block storage, file storage, the fundamentals, and how you do the performance testing and get the right results. So you can watch them on demand. They're available now. Again, go to the SNIA website, go to the ESF forums, and then go to the Webcast page, and you will find those.
And on that subject, there's a new one coming up at some point. We're going to talk about the workload specifically.
Okay, very good. That's good to know, Mark. Okay, after this webcast, and we still have a couple more minutes, we'll cover a few more questions, but please do rate this webcast, give us feedback. The webcast and a PDF of the slides will be available immediately after we end the webcast. And about in a few days, maybe a week or week and a half, we'll post a Q&A answering all the questions, including any questions we don't get to live here on the webcast. You can follow us on Twitter at SNIAESF. And if you're wondering about some terms that we forgot to explain, an acronym, you can find these in the SNIA dictionary, which is again on the website. So that said, we have more questions, and let me take them back to the presenters. So one question that can be for, that's probably mostly for Mark here, is are buffer and cache made of the same type of storage, or can they be made of different kinds of storage?
Excellent question. Theoretically, they're all made out of silicon, so that's really the thing that unites them. In reality, buffers are something that a lot of times built into either a physical device or something that's kind of out of reach and out of much control, something like on the switch, for example. Whereas caches are a little more dynamic, where they could be redefined and they're a lot larger. So technically speaking, you can always think that caches, for simplicity's sake, are made out of RAM capacity and are higher in the stack, whereas buffers are these temporarily bits and pieces right on the silicon on the chipset somewhere inside the hardware that you are using. And their capacities don't match, excuse me. The buffers are typically very, very little. Caches can be very, very large.
Got it. Okay, that's a great answer. Thank you. Question to Rob. On the priority flow control, if you get something slowed down in one priority, say P1, because you need to pause on that priority, can traffic on the other priorities, like P2 and P3, keep going?
Yes, absolutely.
Okay, that's good to know. And for Dave, we have a question. I think you're the best person to answer this question. And let's see. Does the LUN queue depth include the queue depth that you talked about in your section of the webcast?
Actually, LUN queue depth's a little bit different. I mean, that's what you're looking at is typically out, on the storage device with the LUN queue depth. There could be other I/O, like for instance, HBA may have a queue depth as well. Yeah, LUN queue depth is typically that's definitely a SCSI term, the SCSI technology there. But yeah, the LUN queue depth could be out something that storage target has, and then also it could be something that that the HBA on the host has as well.
Got it. So those would be like a queues for SCSI commands of the HBA or in the storage device itself, whereas the other queues might be queuing up like storage commands or application commands rather than SCSI commands.
Right.
So one of the ways, if I can interrupt on that one, if you think of that image that I had in there showing the entire solution in a test and how caches live everywhere, if you think that way, you may have multiple different queue depths at different point of the life of the I/O going from the application into this drive somewhere.
Correct.
Okay, great. And Dave, another question for you. Isn't a higher queue depth also going to increase latency? So does that mean a higher queue depth might slow down applications because they're waiting longer for the I/O to complete?
Potentially, yeah. I mean, ideally, the smaller the queue depth, the better. It sort of depends. There again, it's on the technology. Some technologies allow I/O operations to complete out of order. So for instance, even though you submitted the I/O, this is something, for instance, that MDM Express allows. That if an operation completes, sort of a newer one completes faster than an older one, you will get that completion back. But typically, yeah, that is a problem with when you're looking at IOPS versus latency. Ideally, you want something that's really fast, that you can have a small queue depth and you reach your maximum IOPS, with a very shallow queue depth. But unfortunately, that isn't always the case.
Okay, good. Okay, so it requires some So I guess it requires some modeling or tuning to get the right queue depth for best performance.
Yeah, and actually even having multiple queues, that is one usage of it, with an arbitration model. If you had multiple queues and those queues were associated, with, maybe some faster media on the back end, that'd be another way to achieve, both low latency and high IOPS. It's always a trade-off.
Okay. Good. Mark, I think we have time for one more question, and we have 2 or 3 questions here about size. And so I guess it's the age-old question, does size matter? And one question came in, just says size, question mark, but actually a more detailed question is, question on cache, what is the right size for the cache at each point? You showed cache in different places. How do we figure out what's the right size of cache?
Great question. Again, I love these questions very, very much. The answers, though, you may not like, because this is one of those things when you come back and say it depends. The real favorite answer of anybody who's in the performance community. The reality is that cache needs to be there for a benefit. And once one thinks about what kind of benefit the cache brings and transposes that benefit to the workload, that's when the answers come up. Does it make sense to increase cache or not? So going back to a little bit on the basics, if my workload is going to have a good read-hit ratio, meaning a workload is going to ask for data and data is going to live in cache, and that's a good thing. Therefore, having larger cache is a good thing. If the workload is going to be all right with the fact that cache is going to maintain data for a little longer before it's committed to the disk, that's, again, a good thing, then the size of the cache should be increased. However, if the workload is all about writes, and it doesn't really care about the response time on those writes, cache is not necessarily going to be a good thing, and increasing it doesn't give you anything. You may want to use that space elsewhere. Similarly, if the workload comes in with really large IOs, it's just going to be overwhelming the cache faster than there's any benefit. Again, increasing the cache may not necessarily give you the benefits you seek. So in general, if the workload is cache prone, meaning it's going to be positive with increasing the cache, then having that cache increase is a good idea. If, however, it isn't, increasing the cache is not going to bring you the benefit, and therefore you may want to shrink it.
Okay, great answer. So it depends, and that's a fairly nuanced it depends answer. So we're now just a few minutes over time, and there are several unanswered questions, but what we're going to do is we're going to answer those, put all those questions and answers into a blog and post that to the the SNIA ESF website. At this point, I'd like to thank all our presenters. So a big thank you to David, to Mark, to Rob, as well as to everyone for attending. The recording and the slides will be made available right after this webcast concludes. And again, in about a week, we will then post all the questions, answered or unanswered questions with answers, as a blog. So again, thank you everyone for attending. This has been a great webcast, and we look forward to seeing you all again at another SNIA webcast in the near future.
Thank you, everybody. It was a pleasure.
Thank you, everybody.
All right, this now concludes our webcast. And again, please visit the SNIA ESF, please do provide feedback, your feedback on the webcast, and for more information, visit the SNIA website.
And don't forget to rate us. Give all 5s.
Thank you, Mark. Yes, give Mark all 5s. All right, happy Valentine's Day, everyone.